Okay, today I also want to do something that's not in the notes, which is Cayley numbers, and the exception will be G2. So Cayley numbers are fun. Has anyone computed with Cayley numbers here? No? It's tricky. Okay, but I want to just do a few more things in the example section.
One more question. When we say a Cayley number is the same as octonion?
It's the same, just a different name for the same thing. I don't know whether there are two names for it. It's the same thing. So the first thing was something about the fundamental group. Or the classical group, what is a fundamental group? So I think I mentioned this before. It's supposed to be Z when n is equal to 2. Z2 when n is bigger than 2. And SUN is simply connected. UN has pi 1 equal to Z. And SPN is simply connected. Okay. So I'll do one of them. Maybe let's do SON, because that's probably maybe the most interesting. The other proofs are similar. So first, if we know SO2 is a circle, so certainly pi 1 is equal to Z. And the next value, when n is equal to 3, SO3, so we saw on Wednesday that's RP3. So pi 1 of that is equal to Z2. And now we'll do induction. So for this I have to use a couple of things. The first thing, say if I have a group G which acts on a manifold, and I say it acts transitively. If for 2 points in M there exists an element G which goes from one point to the other. Then I say it acts transitively. If that's the case, I can describe the manifold in a different fashion. So I look at the isotropic group. So those G and G which fix a given point. So that's for the moment just fix one point in this discussion. That's of course a subgroup in G. It's closed because it's defined by an equation. So this implies that if I take the quotient, this is a manifold. And this manifold one can identify with M. So there's a natural map from G mod G P naught to M, which takes, so I view this here as a set of cosets, the usual fashion, right? So what's the point here? It's a coset, G times GP naught. And I take that to GP naught. So notice that if I take an element of the coset that fixes the point G naught, so G times something here is indeed the same thing. So it's well defined. Right? So. And it's either check it's one-to-one, it's onto because the action is transitive, and it's a diffeomorphism. So if a group acts transitively on a manifold, you can always write it as one of these homogeneous spaces, as a set of cosets. So you probably have seen that before. Another fact I need is about something from topology. If I have a forbation, I have a long homotopy sequence. Of the homotopy groups. This is induced by the maps given the forbation. You know how it goes on? What's the next group? Have you seen that before? Homotopy of a vibration? Plus 1 or minus 1? Minus 1. Yes. Pardon? Fiber, yes. How does that go again? Some kind of boundary map, right? So of course this then comes from pi I plus 1 of the base. There's an easy way to describe this map. I forget now, but anyway, this is you can continue both directions. That's a sequence, that's a homotopy sequence, and now I can apply this to the situation where but I want to do induction, so I have SON minus 1 contained in SON. SON acts on the unit sphere inside Rn via rotations and acts transitively. But if I have a vector, I can take with a rotation any vector into any other vector. Even more than that, by definition, SON can take any frame, any orthonormal basis into any other orthonormal basis. It's one way to characterize SON. So we can certainly take any vector into any other vector. And what's the isotropy? Say isotropy you see at the North Pole is just the subgroup that is embedded like this. Okay. So I get that by this discussion over there that SON divided by SON minus 1 is equal to SN minus 1. So from this I then get a vibration which is, so in general if I have say a subgroup H inside G, there's always an inducer of a vibration from H to G mod H. So that's a vibration. And now I can apply this to my situation over there. I have SON minus 1 contained in SON, which goes on to SN minus 1. And now write down the homotopy sequence. We're interested in pi 1, so we want to look, say, at pi 1 of SON minus 1 into pi 1 of SON into pi 0 of Sn minus 1, and it comes from pi 1 of Sn. Sorry, on what am I doing? To pi 0 the fiber, right? Well, but the fiber we know is connected. And here is then what? Base 1 more of the base, pi 2 of Sn minus 1. Right, we know that we want to do inductions. We want to go from, SO3 has pi 1 equals Z2, and then we want to go to SO4 and so on. So we need this only when n minus 1 is greater or equal to 3. And we want to go from SO3 to SO4. So n is greater or equal to 4. So pi 2 of at least S3, that's 0. And pi 1 of S3 is also 0, so these groups are 0. That means this is an isomorphism. Okay. So that's it. Right? So SO3 is in the SO4 and so on. by induction. I see they all have the same homotopy group. You can ask, say, what does a representative look like? Right? So, can I visualize that as what rotation is it? Sometimes that's useful. So pi 1 of SON is equal to Z2. So there must be a loop inside SON which is non-trivial. So twice times it is trivial. So what does that loop look like? So it's a one-parameter family of rotations. Here, this inductive argument, this was an isomorphism where this sits inside the bigger one as a block, in this kind of block form, right? So if I can try to understand it inductively, pi 1 of the big group lies in pi 1 of the smaller group. So let's go down, see how we can represent it. For this, we can look at the sequence maybe for n equal to 3. So what happens when n is equal to 3? Pi 2 of S2 I get Z. Pi 1 of SO2 is also Z. Pi 1 of n equal to 3 of SO3. That's my Z2. And what's the next one? Pi 1 of is 0. Okay, right. So that's also an exact sequence. So what does it say? It says that this one is onto. So it says that pi 1 of, what was this? This was pi 1 of SO2 to pi 1 of SO3 is onto. So that means a non-trivial element in SO3 I can represent by the generator in SO2. So I can just look at my matrix as something that sits inside a 2x2 matrix. And for a 2x2 matrix, what's the generator? It's just a rotation by angle 2 pi. So here I could say, well, let's look at R theta here. 0, 0 identity, where R theta is usual rotation matrix. So that's what the generator looks like in pi 1 of SON. Twice times that is 0, which is not obvious. Right? Well, there's a way to visualize this. So y is in SO3 already. So I rotate by 180 degrees in R3. That's non-trivial. And I claim twice times that is trivial. How does that go again? Something like... okay, that's 180 degrees. That's twice times that. That's a picture. For physicists, that's a proof. Okay, so that's this one, and the other ones are similar. By the way, so the relationship between these two groups, which I think is one of the exercises, is U1 is diffeomorphic to SUN cos the circle, but not isomorphic. Why is it obvious they aren't isomorphic? What's something simple that I can differentiate them with? Well, it's one of the exercises. Maybe we can discuss that at some point. This diffeomorphism is kind of fun. That's nice, not isomorphic. What is true is that there is a homomorphism, which is an n-fold cover. So I want to relate the group structure, really one is a cover of the other. But if I want to compare the manifold structure, then they're the same thing. So for example, now of course this now follows from this fact here. But either one I can do inductively in the same way I did before here. Okay, so that's pi 1 of the classic groups. Remember we had the polar decomposition theorem, so pi 1 of all the groups we saw follow from this. Now we know pi 1 of all the classical groups. And there's one proposition I still want to prove, which is kind of fun. I didn't find in the book, I forget where I found that, but it's a very nice proof. Part A, which one? Which one should I do first? SL4C to SO6C. So clearly there's a two-fold cover. Homomorphism, covering of D groups. And then B is that this cover then induces something from SU3 to SO6. SU3 certainly has determinant 1. Real orthogonal lies in complex orthogonal. SU4, sorry. Inside SU4 I have an SP2. And that goes to, I claim, to SO5. So these are all two-fold covers. And we already saw that these are simply connected, right? So this is like the universal cover of SO6 and SO5. Right? So in our language, this would be like the spin group. This is spin 5. And this is spin 6. There is an abstract proof one can give, which is not very satisfying. So if you know a little bit about Lie algebras, you can at first convince yourself that, say, this Lie algebra and this Lie algebra is the same thing. For this, you look at Dynkin diagram. They have the same Dynkin diagram. On the left, it looks like this. So if you know this language already, that's the left, that's the right, that's the Dynkin diagram of this one here. Same diagram, they must be isomorphic. So now the Lie algebras are isomorphic. That means that the Lie groups should somehow be related by covering space theory. I know this is simply connected. So that's a unique, simply connected Lie group with that Lie algebra. Right? And when I divide by the center, the only way so, and I know pi 1 of SO6 is Z2. So there must be two for cover like this. But there's only one way to do this because the center here is Z4. So I have to take twice the generated in Z4, divide by it. I get the Lie group with pi 1 equal to Z2. That's the only one. So it must be SO6. So they must be covering like this. So that's a proof without doing anything. But of course, after you know a lot of theory. So I don't know who anyone has seen it before. But there's an explicit map. That's really very nice. So let's look at A first. The other ones follow from that. So I start with C4. So I have C4. And of course, SL4C acts on C4. Kind of strange, right? You have to go from a 4x4 complex matrix to a 6x6 complex matrix. So how do I make a 6x6 out of a 4x4? Same here, right? The 4x4 unitary matrix must go to a 6x6 orthogonal one. So the way one does this is that I look at the exterior power, lambda 2 of C4. That's 6 dimensional, so I can regard this as C6. Okay. There's a natural way I can now go from one to the other. So if I have some map, some linear map from C4 to C4, I get an induced map from lambda 2 C4. Just in the obvious way, take V wedge W goes to AV wedge AW. So exterior powers are natural. Let's see, what should I observe next? I want to put an inner product. So on C4 I have an Hermitian inner product. Like this. Of course, this I will define with a Hermitian inner product. These are isometries, right? So I'm going to use a Hermitian inner product, and I claim then I get an induced inner product on the exterior power. So general principle, I have a clean vector space, and the whole exterior algebra has induced inner product coming naturally from the inner product on the vector space. And how does one do that? Let's take a vector space V. I want to take lambda k of V and define the inner product on that.
Take all orthonormal basis of V. Take the canonical base association of the stereo power and declare that the base is orthonormal.
Yes. So that's one way to say it. Say E1 up to En is an orthonormal basis of V. And then EI1 wedge EIK, I less than IK is an orthonormal basis of lambda kV. If you want to compute, there's another formula for that which is very useful. Namely, I want to say the inner product between V1 wedge VK and W1 wedge WK. Right, so what's that inner product? Have you seen a formula for that?
Some kind of determinant.
Yep. Determinant. What can I do? Take all the various inner products and let ij go from 1 to k. 1 to k. It's got a k by k matrix, all possible inner products. Take a determinant of that and claim this inner product and this one is the same thing, which is kind of clear, right? If I take an orthonormal basis and you take only wedge products of orthonormal basis vectors, if I choose the same thing here, that's the identity matrix. If I choose a different one, well, then you have to convince yourself this matrix has determinant 0. So anyway, there's two different ways of looking at this kind of inner product. So lambda 2C4 has an inner product. So it also has a Hermitian inner product again. Notice, for example, say if A respects the inner product on C4, this implies that lambda 2A respects the inner product on C6, on lambda 2 C4, which is the same thing as U6. Right, by this formula here, what does A do here? So A of V wedge, well, let's see. Use the inner product, right? So let me just say it in words, right? I multiply all of these vectors with A here. First, A times this is just a wedge power of all the A's. I put the A's in here, respects the inner product here, it's an isometry, that's the same thing, so I get the same thing. So now this formula here is very, very useful to see this. What else can I say? Let's see, how can I go from here to here? So this here is defined by a symmetric bilinear form, right? So this here preserves A. Symmetric bilinear form. Not Hermitian, right? So symmetric bilinear form. And I claim there's a natural one on lambda 2c, right? So there's a natural one called alpha. So what is a natural map like this? Take a 2 form, take another 2 form. What can I do? Wedge them together, right? I'll end up in lambda 4 of C4. So and that's canonically isomorphic to C. Right? So that's clearly bilinear in omega eta. I notice that it's also symmetric. Because these are 2 forms. If I switch forms of even degree, I don't have to pay with a sign. So it becomes a symmetric bilinear form. And that means I can regard SO6C as maps that preserve alpha. Okay. So let's now do part A here. So we have a natural way to go from 4 by 4 to 6 by 6. So take an element in SL4C. I take lambda 2A. That now goes from lambda 2C4 to lambda 2C4. And I want to claim that if that A is equal to 1, right, here we have SL4C, so I assume the term is equal to 1, then I want to claim that it preserves alpha. And if it does, then if it preserves alpha, I would land up in SO46C. Let's do this computation. So what's alpha of omega eta of how do I want to say that? Yes?
How do you see that the ones who use 6 preserve alpha
Not yet. Not yet. We don't see that yet. We want to do A first, and then we're going to see why this is true. So right now, just think of the term 1 matrices. I want to claim the image lies in SO6. I'm going to come back to these later on. So I only know I see the term is equal to 1. Right? And I want to show preserves alpha. So what's alpha of A omega, A eta? Right, I have to show it's in a symmetry with respect to alpha. So well, that's A omega, wedge A eta.
And if you see it in one sensors, it will be evident that the determinant comes out.
So this is what? Dat A of omega wedge eta. Right, I have a linear map which on 2 forms. This now is an induced map on 4 forms. If I have a linear map on 4 forms, it induces a determinant. Okay. So that means if that A is equal to 1, so if A lies in SL4C, this implies that A lies in SO6C. So that's my map from here to here. Let's call it pi. So pi takes A to lambda 2A. Now I claim pi is a homomorphism. So I want to show it's a twofold cover, right? That's our goal, a twofold cover. First, you observe it's a homomorphism. But if I take pi of the product, how was it defined on V wedge W? I take ABV wedge ABW. Okay, I can break that up. First, take out the A. So that's A of BV wedge BW. And now I can take the B out. So that's AB of B wedge W. So pi of AB is AB. So it's a homomorphism. To see what's the covering, I want to compute the kernel. Right? What's the kernel of pi? If it's 2 for cover, it's supposed to be C2. So what does that mean? So matrices A of determinant 1 such that pi of A is the identity. So what does that mean? It means the induced map A so induced map on the wedge product, right? A V wedge AW must be V wedge W for all VW. Pi takes the matrix to lambda 2 of the matrix. For that to be in the kernel, it must be the identity on all of lambda 2 C4. So when is that the case for all VW? So we want to claim it's Z2, certainly when A is plus or minus identity. This is true. Right, so one concludes it's plus or minus identity. And what's the best way to do that? So this was A of V wedge W. Okay, I can think of V wedge W sitting in the two planes spanned by V and W. Right, it's the wedge product of two vectors in that plane. It's supposed to pay that plane to that plane. That's what it says. So it's a linear map, so this implies here that A takes two planes to the same two plane. So no matter what two plane I take, it takes a two plane to a two plane. So I can do the following, say, take two planes that intersect in a line. This is preserved, the line must be preserved. And of course, any line I can write as intersection of two planes. So this means A preserves lines.
You could also diagonalize A.
Why?
Because you're in C.
You are in SL4C. Can I diagonalize such matrices? Can I diagonalize such matrices? Not necessarily, right? They have some kind of Jordan canonical form. But you can't. Just because a term is one doesn't mean you can diagonalize them. But this already more or less means you can diagonalize them, right? It takes any line to itself, no matter what line I choose. So that means that it takes in particular the coordinate lines to themselves. So each coordinate line gets taken to itself. So it only means the matrix of the diagonal. Right, say maybe lambda 1, lambda 2, and so on. Now I want to say that all the diagonal entries are either all of them 1 or all of them -1. So it would be sufficient. Well, let's see, they're all the same. I can choose many other lines now in order to see what happens. Or we take E1, so let's see why are these two the same. I take E1, E2, preserves E1, preserves E2. Let's take the diagonal. Preserves the diagonal. So A of E1 plus E2 must be some new multiple of E1 plus E2. But this here is lambda 1.
Any two is 1.
Pardon?
The product of any two is 1.
Why is that?
Because the equation you have on the right.
Pardon?
Because on the equation you have upright.
Ah, yes. So lambda I, lambda j is 1. Ah, that's a good idea. And the product of all of them is 1. Is that enough?
You take a third one and you divide. You have that. The first coincides with the third.
Ah, yes. Very good. Okay. So all the diagonals are the same. Lambda times identity. What else?
And the square is 1, so they must be as well.
Ah, there we go. Yes. And the square is 1. Lambda plus minus 1. Very good. Okay. So our kernel is Z2. Last thing, I have to observe that the dimension of SL4C is equal to the dimension of SO6C. So I'll leave that up to you. So what do I have now? I have a homomorphism of the same dimension. Kernel is Z2. Why is that a covering?
Because the differential is isomorphism.
Because the derivative, since the kernel is Z2, the derivative has no kernel. It's injective, same dimension. It's an isomorphism. It's an isomorphism. Homomorphism is a covering. Right. Okay, so we're done with A. A is a covering. Now I want to use that to say that this implies B and C. So these are all subcategory others, so I take the same map, just the induced map. So what remains to be shown is that if I take something in SU4, then the image in here actually lies in SO6 instead of in SO6C. So it's actually a real matrix. Also, if A lies in SU4, I know two things. So that A is equal to 1. So it means that lambda 2A, of course, lies in SO6C, where we saw that. And because it preserves emission in a product, means that lambda 2A preserves the inner product on lambda 2C4. So lambda 2A is an element of SO6C intersected U6. Right, so it's both unitary and it also lies in SO6C. So I want to claim that this implies it lies in SO6R. So let's think of this in matrix form. What does this mean? A times A bar transpose is identity. SO6C is A times A transpose identity. It was not skew Hermitian, the inner product was just skew symmetric. So this, of course, together implies that A is equal to A bar. So the matrix is real. So the real matrix in SO6C lies in SO6R. Okay, since the kernel here is Z2, the kernel here is Z2, again, they're the same dimension, it's a covering. The last one is kind of fun. So now I want to, in addition, assume it lies in SP2. Then I want to claim it must lie in SO5. So that's, as a subgroup in here, it must fix the vector. Right? If I can show the image fixes a vector in here, it must lie in SO5. So what's the fixed vector? How can I describe something lies in SP2? So now I have to, you have to remember something. So which matrix is in SU4 or in U4? Lying in SP2 as long as it preserves the symplectic form. So first I can say SU if I want to. So this was this computation. If I look at the quadratic inner product, that's a complex inner product plus a symmetrical linear form, skew symmetrical linear form. Right, so the complex part is Hermitian and the rest is skew symmetric. Skew symmetric means it lies in SP2C by definition. So if something preserves this here, it must preserve this part and this part separately. This means like it lies in U4. This means it lies in SP2C. And then the reason I can put the S there is that these matrices have determinant 1. So it actually lies in SU4. So what does that mean? That means I have another structure. So if A lies in SP2, I have another structure, and it lies in here. Right, so means there exists, let's call it omega, skew symmetric, and A preserves it. So omega AX AY is equal to omega XY. But omega is skew symmetric on C4. And so omega goes from C4 cross C4 into C and is Q. There's another way of looking at that, a skew symmetric 2 form on a vector space in general. If you have a skew symmetric bilinear form in the vector space, you can regard it as an element of lambda 2. So I claim this means that omega is an element of lambda 2 of C4. How does that go again? How do I go from omega to something like this? I could do like as follows. Let's define it by taking the inner product with anything. If I tell you what all these inner products are, I know what omega tilde is. And what should the inner product be? Omega applied to V. To V batch W. To V comma W. That's a complex number. It's Q in V and W. That makes this well defined, because that is Q. And since I tell you all of these, this is a well-defined element. So now I claim that I can now use this with something lies in SP2. I have to find a fixed vector. So I claim that this omega tilde in lambda 2C4 is fixed by A in SP2. Right? What do I have to say? Just plug it in here. Let's see.
It must be equivalent to what you wrote that A preserves W.
Yes, absolutely. So if I replace maybe V and W also by
The induced A is QA in W2 puts the A inside, and that should happen.
why am I done now? Is that what you wanted to do? Why am I done?
Because on the left you have A acting on W bar.
This here?
That would be the same of
Why?
the induced morphism of A acting on W bar. Yes. Applied to any two vectors.
Why is that?
By definition of how you use the morphism. A of the form goes inside.
Ah, yes. Okay, so that's therefore then the same thing as omega tilde V wedge W for V and W, and this implies that A fixes that vector. Right? And this omega tilde was an element in lambda 2 of C4. Right? Here I was in lambda 2 of C4. To line here means it's real, so it lies in SO6. And now I have an element in SO2C4, which is fixed by this element, so it lies in SO5. Kernel again is Z2, have the same dimensions, so it's a covering. Okay, so same kind of argument. So it's kind of really pretty proof using the exterior algebra. Okay. These are the only covers between classical Lie groups that we saw. There aren't any others. Right? If you look at all Lie groups we saw, there aren't any other covers, only those. Another thing that illustrates is something about the center of the spin groups. What do we know? We saw spin 3. Spin 3 was S3, right? You had a 2-fold cover from so spin N was a 2-fold cover SN. So for a 2-fold cover of SO3, we saw it was S3, and this is plus or minus 1. So it's Z2. What's the center of spin 4? We saw spin 4 was S3 cos S3. Right, we had a 2-fold cover last time from this onto SO4. And this is a Z2 cos Z2. Now we can see what spin 5 is. So this here says that spin 5 is sp2, that's my 2-fold cover. Center of sp2. That's again only diagonal matrices, so it's plus or minus identity. So it's isomorphic to Z2. Center of spin 6. So spin 6 wants to cover this one, that's SU4. So it's the center of SU4. That's diagonal matrices of determinant 1. So that's 4th roots of unity. So this is sort of all A identity with A to the fourth equal to 1. So that's isomorphic to Z4. So Z2, Z2 cross Z2, Z2, Z4. And now we'd like to guess what is the center of spin n in general. First we can see how large is it. So spin n is a 2 for cover of SON. That's a 2 for cover. Here the center, when n is odd, the center is trivial. That means here it must be Z2. The image of the center is the center. That's a 2 for cover. Here it's trivial. That must be the kernel then, only Z2. When n is even, the center on the right-hand side is Z2 minus identity. So I have a center here with 2 elements. I take an image under the cover, because everything in the kernel lies in the center also. So that's another Z2, so at least that's order 4. There's 4 elements in it. 2 from the kernel and 2 from the image in the center here. Okay. But which group it is, this doesn't tell me. I mean, the cover, this homomorphism doesn't tell me which one it is, and you see there's a difference. For spin 6 it's Z4, and for spin 4 it's Z2 cross Z2. And that's consistent. So it's Z2 when n is odd, Z2 cross Z2. So that's also for spin 4, so when n is 4k. And Z4 when n is 4k plus 2. Okay, so that means that something we discussed earlier also occurs in higher dimensions. So what does this mean? But this means something that this is often a mistake you see in the books. Look at subcovers of spin n. How many groups are there with Lie algebra spin n? Right. Obviously algebra SON, right? It's Q-symmetric matrices. It'll be the same thing. So our theory told us, well, look at the center of the universal cover. That's the universal cover. Here it's the center. Then divide by a discrete subgroup of the center. You see when n is odd, there's only one element in there. The quotient must be SON, since I know that SON is a twofold subcover. So when n is odd, only spin n at SON. In this case here, when n is 4k plus 2, what are the subgroups of Z4? It's either trivial or Z2 or Z4. Only possibilities. That means there's only one twofold subcover, because there's only one subgroup of order 2 in here. That twofold subcover must be SO, the orthogonal group. So when n is 4k plus 2, spin n divided by Z2 is SO n. And then I can divide by the whole group, or SO4. Well, that's the same thing as SON divided by Z2. But the Z2 was the center of SON, which was plus or minus identity. Right. But now, when in the other case, it's again interesting, because there are three subgroups order 2. Yeah, so it's not clear which one is SON, but there are some others. This here is the low-dimensional case. When we had this discussion, If I divide by 1, 1, I get SO4. If I divide by 1, identity, 1, minus 1, then I get something new. So here the claim is that the same thing happens in high dimensions. So spin 4n divided by, say, 1, 1 is SO4n. Of course, if I divide by the whole center, I get again the quotient of SO4n divided by plus or minus identity. But now I get that's something that is sometimes called SO prime 4n, which is spin n divided by 1, plus or minus 1. So it's now the Z2. Right? So this also has pi 1 equal to Z2. Because the 2 for subgroup of spin n. Right? So there are two Lie groups with pi 1 equal to Z2. They look very similar, but they're not the same, which is not obvious. Whether different or not is not quite so obvious. Here we had an argument we discussed last time that SO3 cross S3 is not the same thing as SO4, right? So in this low dimension we saw that different. Here one has to prove something. So SO4n isometric to SO prime 4n if and only if n is equal to 2. So for SO8 I get the same thing. That's not obvious at all. That has something to do with a special property of SO8. We'll come back to that later. There's some kind of triality principle for 8 by 8 orthogonal matrices. But otherwise they're different. But it's not obvious, right? I mean, there could be some automorphism, some which takes 1, 0 to 1, 1. You have to show it. That's not possible. That's not obvious. Okay. I wanted to do something on one last Lie group, which is one of the exceptional Lie groups. So I want to find G2. So remember there, I think I mentioned before, there are, besides the classical ones we saw, there are a sequence of exceptional ones. And one of the claims I made was that every compact Lie group up to covers is a product of SON, SPN, UN, or one of the exceptional ones. And I want to describe G2. The other ones are hard to describe. For this, I have to look at the Cayley numbers of the ectonians. There are various ways to describe it. So for our purposes, I'm going to do something similar to how I go from write like this. From C, I can go to the quaternions. Right, here I think, of course, of I, and here I think of J. Right? But it always has a property that I add a new element whose square is minus 1. Right? So now I want to do this once more. And that gives me the Cayley numbers. So I do H plus H times epsilon, and epsilon squared is minus 1. And now to be careful how, so now to find a product on it. So let's try to multiply A plus B epsilon with C plus D epsilon. One can think of, say, if I were to write this down here for the quaternions, one could try to guess what it might be, but there's a difference. But if I go from C to H, the components are something that's abelian. They commute with each other. Right? If I go from H to Cayley numbers, the A and B, they don't commute with each other anymore. Right? So I'm losing something. So therefore, the order is going to be important. And here's the order. AC minus D bar B plus dA plus BC bar times epsilon. Okay, that's what I claim. Let's just compare this, right? If I do this for the quaternions, A plus BJ times C plus DJ, what is it? That's AC. BJ times DJ, so what is that? Remember, I can switch them around, but then I have to conjugate. So it's the same thing as B D bar JJ. J squared's minus 1, so it's minus BD bar. So that's the complex part. What's the J part? Sorry, BJC, just write it out. And ADJ. I'm going to pull out the J on the outside. So I get an AD here. Here I have to switch these two, so it's a BC bar. So let's write out. It's AC minus BD bar plus BC bar plus AD. Right, that's how it multiply quaternions. And now you can compare. The order doesn't agree. Right? That's the only thing, a difference. And here, that's the same. The order doesn't agree. So I've switched the order, but that's important because quaternions don't commute. Whereas for the complex numbers, it doesn't matter. Here, I could write any way I want to because A and B are complex. And you need that for things to work out. So let's see what kind of things are okay when I do that. First, I claim that this is a bilinear form. That makes this into an algebra. So I claim K is an algebra over C. Right, what's an algebra? It's a vector space over the reals. On the vector space, you have to have a multiplication. So that's a multiplication of this K numbers as a vector space over the reals. And also, in this case, I have A lies in the Cayley numbers. So usually when you talk about algebras, the unit doesn't always lie. There isn't always a unit. So here there's a unit. And clearly when A is the unit, when A is 1, that's the unit in the multiplication. So this naturally has a unit. But now I have one more structure, and they may have a norm. So I want to declare what is the length of A plus B epsilon. Well, so if I think of what should it be, if I think of a quaternion here, what's the length of the quaternion? It's length of this squared plus length of this squared. Right? Here it would be the real part squared plus the imaginary part squared, and so on. So I'd like it to be norm A squared plus norm B squared.
Does epsilon commute with the quaternion's number?
No, it doesn't. So for example, what is, let's see, what is epsilon B?
Epsilon, on the first line
This one?
Yeah.
Let's see, what's epsilon times b? So I have to interpret this as, this is epsilon, and this is b to multiply. So what does that mean? It means a is 0, and d is 0. A is 0, this goes away, d is 0, d is 0, and b was 1, and c was b. So it's b bar epsilon. So epsilon b is b bar epsilon. Okay. Let's do another computation which kind of shows that this here really is a good. So a couple of things we want to check. Maybe the first one is kind of useful. Let's say I have a Cayley number, and I claim the norm x squared is x times x bar. What is x bar? So I have a plus b epsilon. What should be a conjugate b? Pardon?
You conjugate everything, coefficients and e.
So what do I get? A bar
B bar
minus?
B bar.
No? I have to write in this form again, so it's a quaternion plus quaternion times epsilon. So everything you have to always write in this form to be in the Cayley numbers, right, by definition. Think of it this way here, right? If I take, pardon?
B epsilon.
Minus b epsilon.
Minus
Right.
B epsilon.
Like if I take here a conjugate, this of course a conjugate, and this here is j and k, so I conjugate everything, the coefficient here. So it should be minus b epsilon. I now claim in this language x times x bar is a norm squared. Remember, this is how we often compute in complex numbers or in the quaternions, that the norm is a number times a conjugate. So let's carry it out, just to see how the multiplication works and why this order is very useful. A b epsilon times a conjugate, a bar minus b epsilon. So I'm just going to do this carefully. So AC, that's a bar. What's the next thing? Minus d bar b. That is b bar times this. Right. And what's the next part? dA, d times a. So that's a times minus b. And what's the next one? BC bar, b times the conjugate of this. So that's b times the conjugate of this plus BA. Did I do the order correct? I want to claim this is norm a squared plus norm b squared. This, of course, is true, so this I would like this to be 0. Let's see. dA minus BA. And what order? We have to be careful about the order. First, the D, that's minus B, and then the A. One way around. It's important. The order is very important, right? Now they cancel. Right, so this is a good formula for the norm. Okay. And kind of, you can now see the multiplication, why the order with matches actually very good together. If I change one of these, this wouldn't be true. Another thing you have to check, and I'm not going to do all of them. That rule holds, which you know for quaternions. And the important part is that norm xy is norm x, norm y. So multiplication preserves a norm. That's a somewhat tedious calculation using this fact here. Right? So this is xy bar. I have to multiply according to the definition, and so on, and use a conjugate. So you can just crank this out. This is like 5 lines or so. But nothing deep, just exercise in applying the definitions. So if I add this to it, that's called a norm division algebra. So an algebra which has a unit and satisfies this property is a norm division algebra. That's what it's called. Well, it's a division algebra we're going to see in a minute. So division means I have to divide, right? So I can solve equations. I have an inverse, which a priori is not true, but it's not clear yet, but it's going to follow from this property here. And then there's a theorem of Hurwitz, which says that a norm division algebra implies that A is R or C or H or the Cayley numbers. Those are the only norm division algebras. Of course, for these three, that's something we used already. For those three, it certainly preserves a norm. Okay, that's the definition.
So, normal, this algebra is need not to be associative.
That's correct. That's correct. But that's maybe another fun exercise. Let me see that it's not associative. Let's look at epsilon times I times j, and I claim it's not equal to epsilon ij. Ij is k. This is epsilon k. What's this here? What's epsilon times I? Well, we already did a computation here, right? Epsilon times b is b bar epsilon. So epsilon I is minus I epsilon times j. This here is k bar epsilon. Of course, k bar is minus k. That's minus k epsilon. What's this? Now I have to use the rule how to multiply two Cayley numbers. So let's see. A is 0 and D is 0. A is 0, D is 0, A is 0. It's B C bar epsilon. So which one is B? Is minus I. So minus I times C bar. C is J. So times minus J. So it's K. Right, whereas on the right hand side, times epsilon, of course. Right here, I multiply this, and that component was non-zero, so multiply by epsilon. Right, so k epsilon minus k epsilon. It's not an associative algebra. Okay. Particularly if you try to do this once more, so I could say, well, let's do it again another time. If I take Cayley plus Cayley, I can write down this multiplication. It's still an algebra, but this breaks down. So crank it out and see if that's true or not. It breaks down. This is not going to be normed anymore. Okay. So I cannot go one step further. I get an algebra, but not a normed algebra. You may not even get a division algebra, I forget. You can do it. It's a multiplication. It's an algebra, certainly, right? But it's probably not a division algebra.
Is it norm helps?
Hmm?
Is it
Not yet.
And what kind of techniques or theories do they use to prove that?
We'll see that a little bit on Monday. So I want to continue a little bit more to now describe G2. And in the process of seeing what G2 is, we will see the techniques that one uses to prove that. There's something called the Cayley-Dixon process that helps you do that. But let me just define G2, finish it today. So G2 is defined as those linear maps of the Cayley numbers which preserves a product. So automorphisms of this algebra. That's the definition of G2. The simplest one of the exceptional Lie algebras one can write down. It's just the automorphisms of the Cayley numbers. And on Monday I want to derive a few properties of G2. It's going to be compact, simply connected, the center is trivial. It's simple. Particular notice that for combining these two, that means that there is no subcover. Right? I can't divide G2 by something. I just get G2 as a compact Lie algebra as a Lie group with Lie algebra G2. Okay, so I'll do this a little bit, and we kind of see how you can work with these automorphisms. And in the process, we see how one will prove such a theorem. Okay. And then after that, I'll go to general theory of nilpotent and solvable Lie algebras. I try to put it in the notes. I'm not quite sure when. The generalized Heisenberg groups are not in the notes yet either. I have to catch up. Pardon? Say it again? Oh yes, excellent idea. Who volunteers to type it up?